Hello everybody, my name's Iman and SID. Welcome back to my YouTube channel. Today, we're going to go ahead and start chapter 9. Now, the first page of my notes is this kind of overall summary of everything we talked about in chapter 8. So here you have all the reactions we talked about in chapter 8, hydrohalogenation, acid-catalyzed hydration, oxymercuration-demercuration, hydroboration-oxidation, catalytic hydrogenation, halogenation, halogen reactions, anti-dihydroxylation, syn-dihydroxylation, and oxidative cleavage. And for every single one of these reactions, I have a little bit of a profile built for each right here. What are the groups that you're adding? What are the reagents you need for this reaction? And actually, for this one, it's split, right? If you just have a hydrogen with a halogen, then that's mark addition, all right? If it's HX with peroxide, then it's anti-mark, all right? Is it syn or anti? Chiral center considerations, carbocation rearrangements, and for each one, there's a bit of a summary here for all of them so that you can keep this organized. I thought this would be helpful. This is your summary for chapter 8. If you want more details for every single one of these reactions, go check out my chapter 8 video. But if you feel like you got a handle for it and you just want a page refresher, this is that for you. All right, so print this out, keep it with you, and whenever you need to refresh, especially for finals, this is a good summary for chapter 8. All right, so that's enough about chapter 8. Let's get into chapter 9. Here, we're gonna expand and discuss things that are very similar to chapter 8, which was reactions of alkenes. Here, we're going to talk about reactions of alkynes, so triple bonds. All right, we're going to cover the following reactions here in great detail. These reactions are preparation of alkenes, catalytic hydrogenation, two ways. All right, we're going to talk about the dissolving metal reaction. All right, we're going to talk about hydrohalogenation. We're going to talk about acid-catalyzed hydration, Hydroboration-oxidation, which is kind of your base catalyzed hydration, if you will. We're going to talk about halogenation, Ozonolysis, and then last but not least, alkylation. This is going to be very easy if you understood chapter 8. Well, it's kind of very similar concepts, but now instead of double bonds, we're talking about triple bonds. We're going to introduce every topic one by one. We're going to do a couple practice problems, and then we're going to wrap it all up. All right, so with that, let's get started. First thing up is let's learn how to prepare alkenes. Well, alkenes consist of carbon-carbon triple bond. And triple bonds, remember, a triple bond consists of one sigma bond, two pi bonds. All right. The bond angle for a triple bond is 180 degrees. That's consistent with sp hybridization. So whenever you're drawing a triple bond, for example, right here in a molecule, make sure you continue straight, 180 degrees here for triple bonds. Then you can go back to the zigzag notation for single and double bond notation in bond line. All right, so keep in mind, triple bonds, 180 degrees. You have to make sure you're drawing that properly whenever you're drawing molecules with triple bonds. Fantastic. All right, so now, just as alkenes can be prepared from alkyl halides, remember, we covered this alkyl halide. You can prepare alkenes from that. Same thing for alkynes. Alkynes can be prepared from alkyl dihalides. All right, this works with visyl and geminal alkyl halides, but what does that mean, right? So let's stop and define those. All right, these terms, vicinal and geminal, refer to the placement of halogens on carbons. All right, that's very important. Geminal dihalide means that both halogens are connected to the same carbon. All right, look at how both of these halogens are connected to the same carbon. This is a geminal dihalide. All right. Now, vicinal dihalides is where the two halogens are connected to adjacent carbons. This would look like something like this. All right, this would be now vicinal dihalide. For geminal, both the halogens were on the same carbon. For vicinal, they were on adjacent carbons, the two halogens. Either way, you can prepare alkenes from these through preparation methods that we saw with alkenes. You can do alkyne preparation with the same way with dihalides, whether they are geminal or vicinal. So now the question that you would probably be asking is, well, what are the reagents required for this, right? That's an important question to ask. What reagents do I need besides just a dihalide to take alkyl dihalides, and then convert them to alkenes, to triple bond? Then treated with water. Let me repeat that. The reagents you need besides just dihalides is sodium amide dissolved in liquid ammonia and then water. What's going to happen is this process is going to occur via two elimination reactions to take the dihalide to an triple bond, to take it to an alkene. All right, so let's go ahead. Let's do this example problem here together to see this in play. All right. So we have our dihalide. This is a vicinal dihalide because both of these halogens are attached to two carbons adjacent to each other. All right, so we have our alkyl dihalide. We have, look at that, sodium amide dissolved in liquid ammonia and water. So let's go ahead and proceed with this reaction. All right, what's going to happen here is this NH2. All right, this NH2 from the sodium amide is going to come in and steal one of these hydrogens here. All right, this hydrogen is going to dump its electrons here, and this chlorine is going to leave. All right, so with that being said, we formed a double bond right there with our chlorine here. All right, and our chlorine here, on the other chlorine has left to form this first double bond. Then again, all right, your NH2 minus is going to come in. It's going to steal now a hydrogen from here. There's a hydrogen right there. It's going to steal it. That hydrogen's going to dump its electrons there. Halogen leaves. And what do we get as a consequence? Well, what we get as a consequence is this triple bond, and there's a hydrogen here. All right, fantastic. All right, so that is how that works. That is how you can prepare alkynes. I'm sorry. Fantastic. Now, with that being said, just like alkenes, double bonds, alkynes undergo a lot of the similar types of reactions we saw in chapter 8, one of them being catalytic hydrogenation. All right, so we can add hydrogens to our triple bonds to take them to double bonds or even single bonds. So one equivalent of molecular hydrogen and platinum, one equivalent of this can convert an alkyne, all right, to an alkene, to a double bond. All right, two equivalents, if you treat it once more again with hydrogen, molecular hydrogen and platinum, you can take the double bond, the alkene, to a alkane. All right, single bonds. You can completely saturate a triple bond all the way down back into a single bond. Now, what if you want to specifically isolate this cis alkene? All right, you're trying to develop, say, a synthesis pathway. You want to take an alkyne to a cis alkene. That is your objective. Can you do this? How would you accomplish this specifically? Well, what you would need to isolate this cis alkene is a partially deactivated catalyst. All right, and one common example of this is Lindlar's catalyst. Without one, a cis-alkene would be really difficult to activate because it's going to be super reactive towards further hydrogenation. If you are just treating a triple bond with molecular hydrogen and platinum, it's going to want to go all the way to an alkane, a single bond. But if your goal is to isolate this cis-alkene, then what you would want to do is treat it with molecular hydrogen, but then alongside a Lindlar's catalyst. This way you can take an alkyne, convert it to a cis-alkene. All right, now what if you don't want a cis-alkene? What if you want a trans-alkene? Is there a way to accomplish this? Well, the answer is yes. And the reagents used for this reaction are actually sodium metal in liquid ammonia. So if you want to take your alkene to a alkyne to a trans alkene, if this was your goal right here, then what you would need to use for this reaction is sodium metal dissolved in liquid ammonia. Now this reaction is called dissolving metal reduction, and we're going to see the mechanism for this in a second. But for now, let's look at this chart that summarizes the reagents necessary to get cis trans alkenes and even go further to get alkanes, starting from triple bonds. All right, so if you're starting with an alkyne, all right, you can treat it with a molecular hydrogen and Lindlar's catalyst to get cis-alkene. All right. Now, you can also take your cis-alkene, treat it with more molecular hydrogen and platinum if you want an alkane, if you want single bonds. You can do that. Or if you want single bonds right away, you can just take your triple bond, treat it only with molecular hydrogen and platinum. That will also give you an alkane. Now, if you want a trans alkene, sodium dissolved in liquid ammonia will give you trans alkene. You change your mind, you want single bonds, you can treat it further with molecular hydrogen and platinum to get single bonds. Fantastic. Now what we want to do is we want to look at this dissolving metal reduction mechanism. All right, because it's interesting. It's interesting that we can take a triple bond and treating it with just sodium and liquid ammonia can take it from triple bond to a trans alkene, trans double bond. All right, now in the first step of this mechanism, a single electron, all right, is transferred from the sodium atom to the alkene, and this is going to generate a radical anion intermediate. We're not going to worry so much about this terminology because in the next chapter, chapter 10, we're going to talk all about radicals and what they are. All right. And so for that, we're going to leave the details of some of this reaction, which is a radical reaction, to chapter 10, but we just want to give a quick overview for how dissolving metal reaction really works. All right. So a single electron is transferred to the alkyne, generating this radical intermediate, anion intermediate. What we've done is we've given the single electron to one side of the double bond, to the triple bond. We've broken the triple bond. We now have a double bond where one side of the double bond has a pair of electrons and a negative charge, and the other side has a single electron. Now ammonia donates a proton to this radical anion. It generates again, you still have this radical intermediate. Now you have a hydrogen on one side of the double bond, but you still have that one electron lonely on the other side. So we're going to treat it again, all right, where a single electron is going to be transferred from a sodium atom to this radical intermediate so that we can generate this anion, this lone pair with a negative charge on one side of the double bond that we can one more time treat it with ammonia, where ammonia is going to donate a proton to the anion, and then boom, we have our trans alkene. Fantastic, exactly what we wanted. So that is how our dissolving metal reduction mechanism works. Fantastic. So let's do a couple of practice problems here. All right, make sure that we completely understand how to do this. All right, so if we're starting with this, all right, and we're treating it with molecular hydrogen and Lindlar's catalyst, we know that what we're going to be forming here, all right, is cis-alkene. All right, so we got to make sure that what we're drawing here is cis-alkene, right? Because Lindlar's catalyst is going to give us that. All right, so count your carbons: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we have a group attached here at the second carbon. Perfect. That's exactly what we want. Now, if we just treat it with molecular hydrogen and platinum, we're going to take that triple bond, that alkene, and we're going to convert it to an alkane, single bonds only. All right, so we're not going to have any double bonds, any triple bonds. And so our final product will look like this. Fantastic. All right, now, what if we treat this with molecular hydrogen? And this is the equivalent of a Lindlar's catalyst. All right, that's just another way that you might see it written for you either on a test or a homework problem. Do not get confused. This is asking us, this is going to take our triple bond and again produce a cis-alkene. All right, so that means our product is going to look like this, cis-alkene. All right, now if we treat it again with sodium, with molecular hydrogen, and instead of platinum with nickel, it does the same thing. All right, either one of these metals along with molecular hydrogen is going to take our triple bond and convert it all the way to single bonds. And so what that means is our product will look something like this. Fantastic. All right, now we can move into hydrohalogenation. There are 3 types of hydrohalogenation reactions. In all 3, we are adding a hydrogen and a halogen to the triple bond. In the first, we react an alkyne, a triple bond, with 1 equivalent of alkyl halide. All right, in the second type of hydrohalogenation, we react this triple bond, this alkyne, with excess alkyl halide. So more than just 1 equivalent. All right. Now these first 2 reactions occur through mark addition. That's important to remember. It will occur through mark addition. That means that you add your halogen to the more substituted side and your hydrogen to the least substituted side. All right, fantastic. In the third reaction we're going to cover here, we react the triple bond in alkyne with alkyl halide and peroxide. So this is going to occur via anti-mark addition. Okay, so one more time to recap. You can treat this triple bond with just 1 equivalent of alkyl halide. You add your hydrogen and your halogen to the triple bond. It converts to a double bond, and now you have a halogen on the more substituted side, hydrogen on the least substituted side. Sometimes it's equal sides, so it makes no difference. All right, now if you treat it with excess alkyl halide, you're going to take your triple bond all the way to single bonds because you're adding halogen twice, hydrogen twice to take that triple bond to a single bond. And your third hydrohalogenation, when there's peroxide, you're doing the same thing. Adding hydrogens and halogens to your triple bond, but now in anti-mark, through anti-mark addition. Let's do some practice problems with these because that's really going to be the best way we're going to learn this. All right, so if we look at A, we're taking this triple bond, we're treating it with excess alkyl halide. All right, that means to the more substituted side, we're going to just keep adding halogens until the triple bond is a single bond, and hydrogens are going to be added to the least substituted side. What that means is our product is going to look something like this. All right, where our halogens are being added to the more substituted side of the triple bond, and the hydrogens are going to the least substituted side, right? Because excess alkyl halide, no peroxides, results in mark addition. All right, so the 2 chlorine atoms are installed at the more substituted secondary position than the less substituted primary position. Fantastic. Let's go ahead and do B now. All right, for B, the starting material is what? A geminal dihalide, geminal dihalide, and we're treating it with this excess sodium amide, all right, with a water workup. This is going to give us, this is our alkyne preparation. We're trying to prepare a triple bond because we have, look, a dihalide and all the materials we need to take that dihalide and convert it into a triple bond. What that means is our final product is going to look something like this. Fantastic. All right, now let's do, okay, this one is similar to A, so I'm going to let you do C. All right, and D is very similar to B. Let's do E. All right, this is going to be new. All right, here for E, the starting material is a geminal dichloride, and we're treating it with all the reagents we need to give us a terminal alkyne, sorry, triple bond, not alkene. When the alkyne then is treated with HBr in the presence of peroxides, then after we've made our triple bond, we're now treating with alkyl halide, but with peroxide, so anti-Mark addition. Let's do this in 2 steps. All right, our first step here, we're forming a terminal alkyne. So we're going to go ahead, we're going to draw it. This is going to look like this. This is what we're forming in those first set of reagents. Now we go ahead, we treat it with HBr, but with peroxides. Now this is not excess HBr, so only one set of HBr, one equivalent. So that means we're not taking it all the way to a single bond. We're just forming a double bond. We're only adding one equivalent of hydrogen and bromide. All right. So what that means is ultimately we're going to be forming a double bond here, all right, where the bromine gets added to the least substituted side because of the peroxide and the hydrogen to the more substituted position. Now, for this, because it's just one equivalent, all right, of HBr, we're going to get both cis and trans here. All right, cis and trans here. Fantastic. This is going to be the same case even if there was no peroxide. Whenever we treat it with just one equivalent of alkyl halide with or without peroxides, all right, you're going to be forming a double bond. When you're forming a double bond, that means your products are going to be both your trans product and your cis product. Keep that in mind whenever you're doing practice problems. All right, so go ahead and do F on your own now because you have all the tools you need. All right, let me know what you get for the problems we didn't do, and we can talk about it in the comments, or you can send me an email. Now, next up, alkynes are also observed to undergo hydration. They're all specifically observed to undergo acid-catalyzed hydration, and that's what we're going to talk about first here. Now, in this reaction, your alkyne reacts with sulfuric acid, water, and this mercury sulfate reagent to produce a ketone with an alcohol group added via Mark addition. This mercuric sulfate, it catalyzes the reaction and it activates the alkyne towards nucleophilic attack through the initial formation of this mercurium ion. All right. Now, after attack, this mercurium ion is going to be attacked by water to produce an enol, and the resulting compound is called an enol because it has a double bond and an alcohol group. All right, this enol cannot be isolated under acidic conditions because it's going to rapidly convert into a ketone. Now, what is this mechanism that takes us from an enol to a ketone? Well, it's an acid-catalyzed tautomerization, and this is important and will reappear. So now acid-catalyzed conversion of an enol to a ketone occurs through 2 steps. We're going to look at these 2 steps in the mechanism. As a general summary, we're going to say the pi bond of the enol is going to be first protonated, generating a resonance stabilized intermediate, And then that is going to be deprotonated to give the ketone. All right. Now, let's look at this mechanism. First, just to summarize, we're doing acid-catalyzed hydration. You can take a triple bond, treat it with this set of reagents, and what's going to happen is your alkyne is going to get converted to an enol, and this enol is going to quickly tautomerize into a ketone. All right, so these two steps here, we're going to look at the mechanism for that so we understand what kind of products we're going to get with acid-catalyzed hydration. So whenever you treat an alkyne with these set of reagents, you're going to get this enol. All right, this enol, what's going to happen? The pi bond of this enol is going to be protonated, all right, with this acid that you have. All right, you're going to have an acid like sulfuric acid. The pi bond of the enol is going to be protonated. It's going to generate this resonance stabilized intermediate. Now, we've talked about this. This is acid catalyzed. So that means your resonance stabilized intermediate is going to be a resonance stabilized cation intermediate because it's acid catalyzed. This checks out. Look at this mechanism. We're forming this resonance stabilized intermediate that has this positive charge. We've protonated this double bond and as such have generated this positive carbocation here. All right, now we're going to take the lone pairs of the oxygen, form a double bond here, but that means now our oxygen has that positive charge. All right, now the resonance stabilized, this is our enol, by the way, this is our intermediate that we want to take to a ketone. How does this happen? Well, the resonance stabilized intermediate is going to be deprotonated. This water is going to take the hydrogen. Hydrogen's going to dump back its electrons on the oxygen. Look at that. Our oxygen is reforms both of its lone pairs. It loses that charge because it's been deprotonated. And what we have at the end is a ketone. This happens really quickly. Our enol our enol can't be isolated because it converts to this ketone really fast. All right, so you start with an alkyne, you start with this triple bond, with this set of reagents, quickly converts into an enol, which tautomerizes to a ketone. So for acid-catalyzed hydration of a triple bond, you're forming ultimately a ketone. The enol and ketone, just as a friendly reminder, because we've done tautomerization before, the enol and ketone, they're said to be tautomers. They are constitutional isomers that rapidly interconvert through what? What did we see in this mechanism? Through the migration of a proton. All right. This tautomerization is important. And for this, and ultimately, the ketone is the highly favored result of this this keto-enol tautomerization. So, and for our acid-catalyzed alkynes, remember that we're taking this and we're ultimately converting our triple bond into a ketone. Now, an important thing to note for acid-catalyzed hydration of unsymmetrical terminal alkynes, it's just gonna yield a mixture of ketones. We might see this in a few of these practice problems that we're gonna jump into now. Fantastic. Now, this problem set asks us, draw the major products expected when each of the following alkynes is treated with aqueous acid in the presence of mercuric sulfate. All right, so it's telling us we're starting with this alkyne and we're treating it with our reagents for acid-catalyzed hydration. What do we know about this? It's going to yield ketones as products. All right, so that's what we're going to keep in mind as we do a few of these practice problems. We're going to look at A. Now, when treated with this aqueous acid in the presence of our mercury sulfate, this terminal alkyne is going to undergo Markovnikov addition of hydrogen and alcohol across the triple bond. All right. What's our first step? It's going to form an enol. That's what we talked about. So our terminal alkane, we're going to be adding our hydrogen and alcohol to this triple bond, right? That's what an acid-catalyzed hydration is. Hydration implies that we're adding alcohol and hydrogen to our triple bond. We're going to be doing this to our triple bond, but our first thing that this triple bond is going to be converted to before our ultimate ketone is an enol that's not going to be isolated. This enol is going to look, like this, right? Where we've added our alcohol to the more substituted position of the triple bond and our hydrogen to our least substituted position. We no longer have a triple bond. We have a double bond where there's an alcohol on the more substituted side, hydrogen on the least substituted side. This is our enol. This is not going to be isolated at all. All right, right? Because it quickly converts into our final product, which is a ketone. This is our final product. When we take this triple bond, this terminal alkyne, and treat it with acid-catalyzed hydration reagents, we get a ketone. Fantastic. All right. Now, I'm going to let you do B because it's also a terminal alkene. Let's do C, all right? Because C here is going to result in a mixture of products, and I want you to see what that looks like. So we're going to go ahead and try to do C. I'll leave B and D for you to do. All right, so C. What we have is this alkyne. I'm so sorry. If I keep saying alkene, I mean alkyne. We're talking about triple bonds. It's just this vowel that throws me off. Alkyne. We have this alkyne, all right? We have this triple bond, all right? We're treating it with acid-catalyzed hydration. What does this mean? That means you see this triple bond? We're going to be adding alcohol and water, alcohol and hydrogen to this triple bond. All right, now it's unsymmetrical. So that means we could potentially add the alcohol on this side and the hydrogen on this side, right? Because you both have one group on each side, so it's not necessarily more substituted on one side or less substituted on the other. So what we can get potentially, all right, is we've added the alcohol to this side. 1, 2, 3, 4, 5. Ooh, wrong. Alcohol on this side to form a double bond here, and we have our hydrogen here. Or we can do it on the other side of the triple bond. We add our alcohol. All right, so what that's going to look like is that we can add our alcohol here, double bond here, hydrogen here. All right, so if we have a triple bond like this, all right, this unsymmetrical alkyne, all right, we're treating it with acid-catalyzed hydration. We could add the alcohol on this side, hydrogen on this side, or we can do it the opposite way. Either way, we form both enols that quickly get tautomerized to ketones. This is going to give us two different products here. All right, this one's going to give us a product that looks like this. And this is going to give us a product that looks like... Ooh, hold up. Right here. And this is going to give us a ketone that looks like this. All right, because that's where the alcohol turns into a ketone. Fantastic. So for unsymmetrical alkynes, for hydration reactions like this, acid-catalyzed hydrations, you can add the alcohol or hydrogen on either side, and you form both enols, and you get both ketones as products for this reaction. So this is a very important thing to keep in mind. Now, alkynes, again, like alkenes, can also undergo hydroboration-oxidation. The initial product of this reaction is also an enol that cannot be isolated because it rapidly converts into an aldehyde through tautomerization. Here, basic conditions are employed, so what we're getting, this enol to aldehyde conversion, is a base-catalyzed tautomerization. And notice that the order of events under base catalyzed conditions, and we're going to look at this mechanism in a second, is the reverse order under acid catalyzed conditions. That is, the enol is first deprotonated, and then deprotonation of the enol leads to this resonance stabilized anion, right? For base conditions, we're going to, our intermediate is going to be an anion, not a cation like acid catalyzed. All right, you're going to form this enolate ion that is then protonated to generate your aldehyde. Let's look at this mechanism a little more. For hydroboration-oxidation of an alkyne, you're going to form an enolate that cannot be isolated. It's quickly converted not to a ketone, but to an aldehyde. Aldehyde. All right, so let's explore the mechanism for this. We are still taking a triple bond and trying to add an alcohol on one side and a hydrogen on the other. All right. So you form this enol, but that's under basic conditions. So what happens is that the hydroxyl group of the enol is deprotonated. This is going to be deprotonated. What it's going to generate is this resonance stabilized enolate. All right, this negatively charged intermediate. All right, this interconverts. Right, you have this deprotonated alcohol. It's going to form a double bond here, but if you make a bond, you got to break a bond. All right, and so that means you have this negative charge here. This negative charge is going to be protonated. All right, the enolate ion is protonated. What you get at the end is an aldehyde. All right, so this is very important to keep in mind for base catalyzed hydration. All right, or in other words, hydroboration-oxidation of alkyne. You're going to ultimately take your enol, form an enolate ion intermediate, and that's going to be ultimately converted into an aldehyde. All right, so just to help you identify the difference, you start with an alkyne. You treat it with acid-catalyzed reagents, you're going to get a ketone. You treat it with base-catalyzed reagents, you're going to get an aldehyde. All right, so that's really important to note the difference, because especially when it comes down to synthesis problems, which we'll get to later on when we introduce this idea of synthesis in chapter 11, you might need a final product that looks a specific way, and you might need to take advantage of which one of these hydration reactions you would need to employ for that synthesis. All right, so with that being said, let's just jump into a few practice problems. All right, here A. All right, the reagents here, these reagents, all of the ones that you see here are all versions of base catalyzed reagents. All right, so get familiar with these three sets of reagents. All three sets of these reagents tell you that what you're doing is a base catalyzed hydration of the triple bond. All right, so we're going to go ahead. We're going to do A. Okay, we're doing hydroboration-oxidation of a terminal alkyne. All right. What we're doing is we're going to be adding, and by the way, this is through anti-mark. This is very important to know. All right, anti-mark. That means we're essentially going to be adding the alcohol and the alcohol on the least substituted side of the triple bond. All right, so that means the alcohol gets added to the least substituted side, hydrogen to the more substituted side. Now, this is the intermediate. This is not isolated. This is quickly converted into an aldehyde. That is what is going to give us our final product. So we're going to go ahead. We're going to draw that aldehyde with the same number, keeping consistent with how many carbons we have. Here we have 1, 2, 3. We've drawn 1, 2, 3 carbons here, 1, 2, 3 carbons here. This is correct. So this is the aldehyde we ultimately get as our final product. All right, I'm going to let you try B. Let me know what you get. Now, we can move on to halogenation. Alkynes can also undergo halogenation. One equivalent can add a halogen to either side of the pi bond and you get an alkene, or excess halogen results in a tetrahalide mechanism, but actually the mechanism for this is not entirely understood. So good for us, we don't need to learn an extra mechanism because the organic chemists don't know what's going on. All right, so You have a triple bond, you treat it with one equivalent. All right, one equivalent of, say, Cl2. All right, and then CCl4. All right, you're just going to be adding halogens to both sides of the triple bond. All right, trans is usually favored, but you also get the cis form of this, just letting you know. All right, you do get the cis. Trans is more favored though. Okay, but it's good to know because if you're asked to draw all the products, you get cis and trans. Now, you can treat the alkyne with excess Cl2 or Br2 or whatever, halogen 2 you want. And what you're going to get is you're going to be adding 2 halogens to each side of the triple bond, 2 halogens on each side. So you've completely converted this triple bond to a single bond with 4 total halogens, 2 on each carbon. All right, so keep that in mind. Now, for the last reaction, or actually the second to last reaction, we can also do ozonolysis of alkynes. All right, so when treated with ozone followed by water, alkynes can undergo oxidative cleavage. What this means is we're pretty much cutting up this triple bond. All right, when we cut up this triple bond, all right, it gets converted to a double bond where we fix each end with an oxygen. We keep the R groups that are potentially there, but we also add an alcohol group because ultimately ozonolysis of a triple bond is going to result in carboxylic acids. All right, with terminal alkynes, the terminal side is going to get converted to carbon dioxide, but you're going to form at least one carboxylic acid. All right, fantastic. We'll get to a few practice problems for that in a second, but we want to talk about our last topic of this chapter. All right, at the start of this chapter, we discussed the reagent, sodium amide, how it can deprotonate a terminal alkyne. This is very cool because we can take our alkynide ion and treat it with alkyl halide, and the ion will act as a nucleophile. This provides a method to install alkyl groups on a terminal alkene. As you notice, this process, alkylation, is going to be only efficient with methyl or primary alkyl halides, but it's going to be super useful nevertheless for synthesis. So what this means is you take an alkyne, you treat it with this sort of reagents, the sodium amide, and then some sort of R group attached to a halogen like chlorine or bromine or whatever. All right. You can add to this alkyne R groups to the end. So if you treat it with one set of this sodium amide and Rx, then this hydrogen here on this terminal alkene can quickly be converted to whatever R group you want. Usually some sort of small methyl group usually works best, or ethyl, right? Some primary alkyl group. And then if you still have a terminal halide, you can again treat it with one more equivalent. You can be adding 2 R groups of your liking to this alkyne. And this is going to be very, very useful for synthesis later down the line. All right, so we're going to go ahead and do a few practice problems for this because it's really important. Starting with acetylene, show reagents that you would use to prepare each of the following compounds. A, all right, so we're going to start by drawing the starting material, acetylene. All right, this is just going to look like, boom, triple bond. Fantastic. What reagents do we need to treat it with if we want to form one butadiene? All right, this is going to look like this. 4 carbons where you have a triple bond at the end, right? Because 1, this is butadiene. All right, you have 1, 2, 3, 4 carbons, right? Hence the but. All right, and there's a triple bond here at the 1 position, which is why we have that triple bond right there. What reagents would we need to take this triple bond and convert it to this final product? Well, what do we notice? What we notice is we're adding this ethyl group to one side of the triple bond. So all we would need to treat this with is our good old sodium amide, obviously, but then our R group is going to look like an ethyl group attached to some sort of halogen. We can make this iodide. All right, this is the set of reagents we would need to take this triple bond, this acetylene, and convert it to one butene. All right, Fantastic. Let's do C now. All right. C says here, all right, again, we're starting with acetylene. All right, but we want to convert it into 3-hexene. Fantastic. What is that going to look like? Well, 1, 2, 3, 6 total carbons because of the hex. But at the third position, you have your triple bond. So 1, 2, 3. Here we're going to have a triple bond. All right. 4, 5, 6. Fantastic. This has 6 total carbons where at the 3 position you start your triple bond. Notice when we draw our triple bonds, we keep it straight, right? Because it's sp hybridized, it's going to have that 180 degree. You'd never want to draw a triple bond like you would draw a double bond where you would do something crazy like this. That's incorrect for triple bonds. Never draw them like that. All right, so now how do we convert this triple bond to this 3-hexene? Well, look. Notice what is different here. We have added an ethyl group on one side and an ethyl group on another side. All right, so that means we're going to have to treat it with 2 equivalents of sodium amide, where the first one is ethyl, all right, and we could do iodide. But then again, we have to treat it with 1 more round. So with this first round, we've added 1 ethyl group to one side, boom, but we want another ethyl group on the other side. So again, we treat it with the same reagents 2 times to go ahead and do that. All right, fantastic. Try to do the other ones that we have not accomplished and let me know what reagents you get to accomplish B and D and E. All right, now let's do a few synthesis problems, just 1 or 2, to really wrap this chapter up. All right, we're going to go ahead and we're going to try to do A. All right, we're starting off with this starting material and we want to convert it to this cis-alkene. All right, so how can we do this? Well, what we know how to do, all right, is form triple bonds, and from triple bonds add R groups ultimately. All right, so look at this starting material. We have 1, 2, 3, 4 carbons to start off with, but our final product has 1, 2, 3, 4, 5, 6 carbons. All right, so obviously we've added some carbons. We want to add some carbons ultimately to form this final product. All right, let's draw this out. All right, so we know that we ultimately want to get this cis-alkene. All right, and we know how to get this cis-alkene from triple bonds, for example, right? From triple bonds, we know we can treat something with molecular hydrogen and a Lindlar's catalyst to get this. And what this triple bond would look like would 1, 2, 3. All right, so at the third carbon, we would have this triple bond that we convert to a double bond, and then 4, 5, 6, right? Because we have 6 total carbons. In between here, where we see this double bond, well, for the same molecule, we would have this triple bond. Taking this molecule, treating it with Lindlar's catalyst would give us a cis-alkene. But how would we get this alkyne from this starting alkene? How would we do this? Well, let's keep working backwards. This seems to be pretty good for us. Well, if we're only dealing with 4 carbons, for example, 1, 2, 3, 4, right? This is 1, 2, 3, 4 carbons. Well, we actually know how to deal with this. We know how to take this, convert it to that. We just talked about alkylation of alkynes. We can simply treat this, oops, not an eraser. We can simply treat this with sodium amide, all right? And then whatever R group we want to add, which seems to be an ethyl group. So we'll treat it with ethyl and then attach that to a halogen of some sorts like iodine. This would take this 4-carbon triple bond to this. It would add that ethyl group on the other side, and we would get that. Now the problem is, well, how did we get to this molecule to begin with? All right, that's a good question to ask. Well, if we had, how did we learn to prepare alkynes? Alkynes, I'm sorry. Well, we had some form of dihalides. All right, so somehow we need to take the starting material, treat it maybe with extra halogens, Br2 or Cl2 or whatever, what would happen here is we would add bromines to each side of this, all right? And then take this dihalide, treat it with excess sodium, amide, and in liquid ammonia and water to convert it back to a triple bond. This triple bond you can use alkylation to add an ethyl group to, and finally treat with a Lindlar's catalyst to get that final product. Actually, we want to kind of draw this like so that it is concise, triple bond. All right, fantastic. All right, this is our synthesis pathway to take our starting alkene, treat it with Br2 to add bromines on both sides of the double bond. All right, then we do our alkyne preparation method we learned. That's going to take both of these dihalides and right there at this carbon form a triple bond. All right, now what we have is a triple bond and this ethyl group right here. We need another ethyl group added on the other side. We can do alkylation there and add another ethyl group. We get this, our 6-carbon chain where there's a triple bond in the middle. We can treat this with molecular hydrogen and Lindlar's catalyst to get our final product. And this is how you want to approach a synthesis problem. Make note of all the changes and how you know how to accomplish some of the intermediate steps. Start putting it together as a puzzle piece. Now, if you're not feeling confident with synthesis problems, that's okay. Chapter 11 is simply dedicated to building all the techniques and skill sets you need. So we're going to get to synthesis development and synthesis techniques in more detail soon enough. All right, but with that, we come to the end of the chapter. And here, I really like this diagram at the end of the David Klein textbook where it summarizes all these techniques we've learned. Make sure you familiarize yourself with this. But with that being said, we've finished chapter 9. Let me know if you have any questions or comments down below. I'm happy to take any questions, help you with anything. And if you want more problems for this chapter, just let me know. Other than that, happy studying, good luck, and have a beautiful day.